wanted to talk about IP addressing. So we said that at the layer 2 you have a MAC address. And these are assigned by the manufacturer, so it's hard-coded into the hardware. So an IP address can be configured manually. And this is a layer 3 address. So IP addresses sort of is the common addressing scheme throughout the internet. And what does an IP address look like? So if you look at IP version 4, the address has 32 bits. And how many possible addresses could you have? Well, it's 2 to the power of 32, which seemed like a very large number at the time, they were creating these protocols. So they didn't think that they'd ever run out of this many number of IP addresses. But it turns out that they did run out because the internet exploded so much that there were so many devices. So 4 billion devices is not a large number for today's world, because each human being could have several, and nowadays with Internet of Things and so on, every device might also have an IP address. So clearly this many bits is not enough. So people came up with hacks to sort of cleverly reuse IP addresses. Okay, so they were deviating somewhat from the original ideas. But some of the ideas were things like network address translation, called NAT. We'll look at this a bit later. So this is to reuse IP addresses. But how do we write these particular addresses? So we have 32 bits. So we look at them in 8 bits at a time. We split up the 32 bits into 8 bits. And we write each of these as a decimal number. So of course everything is binary when you send out a packet. There are only bits, but to make it a human readable form, we split it up into successive sets of 8 bits and write each of those 8 bits as a decimal number. Okay. So for example, if there are all ones, it would look like this. It would be 255 dot, so we put a dot in between. 255.255.255.255. Okay, and normally an all ones address corresponds to a broadcast. So this is reserved for broadcast. So what does broadcast mean? It means that this packet is meant for whoever receives it. Okay, so you can send out the packet. Normally what any particular host has to do is it has to see whether the IP address corresponds to it, and if not, of course it should ignore it. But a broadcast means that this is meant for everybody. Okay, so if there is something like this in the packet, then all hosts should potentially read the packet. Okay, so if at all you're configuring an IP address in your machine, you should never use something like this. This particular IP address is reserved. It has a particular meaning, that if the destination address has all ones, it corresponds to a broadcast packet. So what other special IP addresses do we have? Well, you might also see 10 dot something. I'm just going to write star dot star. Here I mean anything. By star I mean anything. So an address which begins with 10 in the first octet is a private IP address, and you will also see 192 dot star dot star dot star. So these private IP addresses are also special in that they can be reused in the internet. So you might find somebody with the same private address in IIT Bombay as in IIT Delhi, let's say, right? Or in any company. Anybody can use these addresses within their own organization. Okay, they don't have to worry about it being used somewhere else in the internet. And these are called private IP addresses. Okay, so they are used if you want to set up your own IP network on your own. You're free to use these addresses, okay, which is why they are called private. So public IP addresses should be unique in the internet. Okay, there may be some minor exceptions we look at later on, but essentially a public IP address should be unique. In the internet. So you would want only one host to have a particular public IP address. Because think about it, somebody is sending a packet to somebody and he puts the destination IP address. If multiple machines have the same IP address, then which one is it going to? I mean, you want only a single destination. Right? So you would want public IP addresses to be unique in the internet. So this means that only one host must use that IP address. Okay, so there may be some minor exceptions like any cast, which we will look at later on. But for now, we will assume that all hosts with public IP addresses essentially have a unique IP address, that they don't reuse the IP addresses of other machines. Okay, so what does the IP header look like? So we've seen what a Ethernet MAC header looks like, and an IP header has some similarities, in that of course you have to have a source and a destination IP address. So here is the IP version 4 header. And the way textbooks write it out is in this fashion. They write the bit number, so this is the 0th bit, and they write it up to the 31st bit. So this corresponds to 32 bits from bit 0 to bit 31. Okay, you write it in this fashion. And bit 32 onwards, you write from here onwards. Okay, so actually you would have one long string of bits corresponding to the IP header, but we are writing it 32 bits at a time in this fashion. So the first 4 bits correspond to the version. And in this case, of course, it's going to be 4. But if you have a different IP version like IPv6, the version number would be 6 over there. Okay, Okay, so IPv6 was a solution created for the problem of running out of IP addresses. 32 bits were not enough. So IPv6 has 128 bits. Okay, so that's a very large number of bits, and we don't expect to run out of those many number of bits. Okay, but you never know. Okay, so there is something called type of service. So many of these are not really used that much. Okay, so the idea over here is that suppose the network offered different services, like you say you could, if you somehow said that it's a higher priority packet, maybe it got a particular service, maybe a lower delay or something like that. But if it was a lower priority packet, maybe you're saying that you can tolerate more delays, right? And this field could be used to convey that to the network by putting a particular number here. And this is the length. So this is telling you what is the length of the IP packet. Then there is something called an identifier. So any number can be put in here by whoever is sending out the packet. It's like you can put a unique something which tries to identify this packet, like a particular number. Then there are flags. These are 3 bits. I'll just write 3 over here. And there's a checksum. Okay. And there's a source IP and a destination IP. I beg your pardon, there is something that I forgot over here. There's something called a fragmentation offset. There is a time to live. Protocol. And the checksum is here. And then you have the source and the destination IP. And of course then there are things called IP options. So these are optional. You wouldn't find them in normal most of the IP packets. And of course then there is the data. Okay. So many of the things they found were not really essential, which is why several of these fields have been done away with in IP version 6. Okay, so what we are going to care about now is just a few of these, so we have to be particularly concerned about source IP, destination IP address, protocol. So what is the protocol? It's going to tell you what is the next layer protocol. So if layer 3 gets this particular packet, it has to know which particular protocol is the next one, to whom to hand it over. So for example, 6, if this is 6, it corresponds to TCP, and if it is 17, it corresponds to UDP, and if it is 1, it corresponds to ICMP. Right? What is the time to live? So time to live is an interesting field. So time to live is saying that I want the packet to survive only provided it is this TTL value is non-zero. Suppose it's greater than 0, you want it to be greater than 0, but if it becomes 0, then that particular router must drop the packet. Okay, so this is decremented at each router. And if it becomes 0, then the particular router has to discard it. So this is to take care of cases where you might have a routing loop, and you don't, suppose as a routing loop, the packet might remain forever in the loop, and you don't want that to happen. But so what will happen if there's a routing loop? This TTL will keep decrementing and then the packet will be discarded. Okay. So we will not talk much about the IP options and so on, right? And so we assume that there are these few bytes. So let's count them: 1, 2, 3, 4, 5. So 5 4s are 20. So this is so each IPv4 header is 20 bytes or more. Okay, by default it is 20 bytes, and then it is followed by the data. So this data is the higher layer, which means it's layer 4 and layer 5. Okay, so the TCP header or the UDP header and so on will come over here, followed by the application layer data. Okay. So how do we use these IP addresses, and how do we assign them? So each router has a routing table. And it has a destination and an next hop. And we want these to be small in number. So the total number of IPv4 addresses, for example, is 2 to the power of 32, and we don't want to have a separate entry for each particular IP address. So how might we do that? So let's think about it. So suppose, let's say this is IIT Bombay. So what are the IP addresses going to be here? So suppose I assign a random IP address out of the whole space of 2 to the power of 32. then all these different IP addresses all correspond to machines in IIT Bombay, and somebody further away, let's say some particular router here, will need to know that all those IP addresses are this way, and it would have to have an entry for each of those IP addresses. Okay, so that's the flat addressing, which like we had in Ethernet, and that's a problem because you have one entry for each particular IP address. Okay, so of course we can have fast methods of looking up, but just the table size is also a problem. You need more memory if you have a larger table. So what is the solution? So you might think what we might want to do. So suppose think of these IP addresses as just abc.d, okay, where this corresponds to the decimal number of each octet. And you were to assign, suppose you were given the freedom to assign a chunk of IP addresses here. What would you do so in order to keep this the entries in this table small? Okay, so one way to do it is that if this is the IP address space, this is 0 and I go all the way to 2 to the power of 32 minus 1. What I might want to do is to assign a chunk of IP addresses, all corresponding and all assigned to, let's say, IIT Bombay. So there's a slice of these IP addresses we assign. So suppose I give, let's say, 256 addresses, roughly 256, eliminating the broadcast address and so on. Okay, so let's say that what we allow is let's say 730 dot 52.30 dot star. Suppose we assign this. Okay, so we assign this, let's say, to IIT Bombay. So there is a central organization which would do this in the internet. If you want a chunk of IP addresses, you would approach them and tell them to give you a slice. Okay. So they might say that, okay, this address space belongs to you. So what does this mean? It means that all machines in IIT should have this as the prefix, and different machines can have different numbers over here. Okay, so all the machines will have this as their common prefix, but this would vary from one machine to the other. Okay, so this would give us potentially 256 different IP addresses which we can use within IIT. And how does it help in the routing table, let's say, of some router which is far away? Well, suppose they want to send packets to IIT, they would only have to put in something like this, 730.52.30 dot star. Let's say this is the router 1 and this is router 2. Okay, it would have to put the IP address of this router 2 over here. Okay, so suppose I do something like that. So instead of having, suppose we had 256 machines here, instead of having 256 entries in the table, I just have one entry, and this is what is called the IP prefix. Okay, and so if at all I get an IP packet, I just see whether the prefix in that packet corresponds to this number, and if it is, then I forward it to router 2. Okay, so this reduces the table size. Now in the original internet, they were wondering what should the size of this prefix be. So they thought of this different classes. So they said class A would have 8 bits for the network address and 24 bits for the hosts. Okay, so this would be common to the network. So suppose I give you a class A address, I would specify what exactly these 8 bits are, and I would give you the freedom to choose anything over here when you assign the IP addresses to different machines. So class A networks could be quite large, up to 2 to the power of 24 hosts. And of course class B and class C and so on got smaller and smaller. So here 16 bits for the network and 16 bits for the host. And class C is like what I showed earlier, 24 bits for the network and 8 bits for the host. Okay, and the funny thing is that so long time back, I think when the internet was coming out, the central body which gives out IP addresses, they allocated something like 2 class C addresses to the whole of China. Okay, that is a joke that goes around, right? So of course in that time China was not such a powerful country, but they thought, why would they need more than that many addresses? But of course things are quite different right now, right? So this is an issue. So suppose we are starting, let's say, a university campus. How many IP addresses do we need? Should we have one for every machine or not? And if you have more than 2 to the power of 8 machines, suppose you have 10,000 machines and you want each to have its own unique public IP address, then you might go for something like a class B address. Okay, 2 to the power of 16 would give you enough addresses, right? But if you have more than that, if you have lakhs of machines, then you may want to go for a class A address. Okay. So let's see how we might use these. So first of all, let's talk about subnetting. So suppose a network administrator is given a set of IP addresses, and he wants to divide that within his own institution, and he wants to configure a router to do some sort of routing. So how to divide among, let's say, several LANs, and how to set up or configure an internal router. Okay. So suppose we have a particular class C address, let's say, and there are several LANs. Let's say we have 2 LANs over here, and we are assigning IP addresses to these 2. And our network topology is like this, that this is an IP router. Okay, and let's say this is what the network looks like. So this is some particular router R, and let's say these are its interfaces. Okay. So you are given a particular class C address and you want to set up the routing table over here. You want to do it manually, let's say, and you want to put one chunk of these IP addresses here and another chunk over here. Okay, so how are we going to do that? Okay, so let's say that we have so we have 256 addresses, and let's say we have 50 over here and 50 over here. Okay, we want to have roughly this many. So what are we going to do? So we have this class C address, and this central organization in the internet says that all your machines should have the first 24 bits fixed, okay, according to whatever is given. And let's take as an example 730.52.30, right? And this can be anything. So we want to split this, and again we don't want to do it randomly between here and here, because then it would be very complicated for this router. How would it learn which machine is which side? We don't want to have a very complicated way of doing that. Okay. So what we are going to do is the following. So let's say that we use 1 bit out of these 8 bits. So let me just draw it this way. So these are the 8 bits. And let's say that I use 1 bit to indicate the LAN. So for example, if this particular bit is 0, that means that the IP address belongs to LAN 1, and if it is 1, it means it belongs to LAN 2. Okay, so what I'm doing is I'm equally dividing the IP address space between the two LANs. Okay, and LAN 1, all hosts would have to have 0 here in this bit, and these bits of course I could set arbitrarily for different hosts. And if it is 1, it corresponds to LAN 2. Okay. So to generalize this, okay, so here of course I am saying this particular bit, but in general I could use any bit or any sets of bits to designate to divide the IP address space between different LANs. Okay, so the way I do that is by something called a subnet mask and a subnet address. So a subnet mask indicates which bits to use while deciding to which LAN to route a packet to. So which bits in IP address to use to decide which LAN to route to. So in this particular example, what would the subnet mask be? So it's essentially we are saying you have to look at all these bits of course, and you also would look at this first bit. Okay. So for example, you have to look at the first 25 bits. So how do we specify that? So the subnet mask would be all ones in these positions, and it would be 0 for the rest of them. So this is the subnet mask, and then we have the subnet address. Okay, and the subnet address, let's just say S1 for LAN 1 and S2 for LAN 2. Okay. So what are these S1 and S2 going to be? We'll just see that. So what is router R going to do when it gets a packet? Okay, so suppose the destination IP address is some D. So what it's going to do is, it's going to first check that is D and the subnet mask for the LAN 1. So let's say that M1 is the mask for LAN 1 and M2 is for LAN 2. Okay. So in general, this is what it would do. It would take an AND, so that essentially the mask is going to eliminate bits that we don't care about. So it's here in this particular case, it's going to look at the first 25 bits, and it's going to see that is this equal to S1 or not. Okay, and if yes, okay, so suppose a packet is coming from here. Suppose the packet is coming from here. Okay, I'll just write that here. Packet on interface 1, interface A. Then of course we do nothing. And why? Because the packet belongs to this particular LAN. So what is S1 going to be equal to? You might think, so it's essentially going to be 730.52.30, and it's going to have a 0 over here. Okay, it's actually going to be all zeros. Okay. So if we had to write it as an octet, it would be a 0 octet. Okay. And in case there isn't a proper match over here, that D ANDed with the first mask is not equal to S1, what would we check? So we would first check, is D and M2 equal to S2. So in this particular example, M1 could be equal to M2. That's because we are looking at the same set of bits. Okay, so we can still look at the first 25 bits. But if at all there is a match with S2, and here S2 is going to have 1 in the first bit over here, so it's going to be 730.52.30.128. So the 1 in the leading bit. In that case, this particular packet is meant for the second LAN. Okay, in which case we should forward to the second LAN, which is going to be C, interface C. Okay, so it would go to the appropriate router, which is towards the second LAN. And what if there isn't any match over here? Then that means that particular packet has a destination address which does not belong to either of the LANs, and in which case we are going to forward it to interface B. Okay, so the packet would actually be forwarded this way. It would be sent this way to this router and go onto the external internet. Okay, so of course these are simple examples, and you could of course think of having different masks and so on, right? So you would have to decide which IP addresses are on which LAN, which set of chunks, and use an appropriate mask and a subnet address for those particular LANs. Okay. So this is how we would do subnetting. Now there are situations where we may want to do the opposite. So it's not that we are given a set of IP addresses and we split it among multiple LANs, but we may actually want to combine several sets of IP addresses, several slices. So if you think about it, so suppose this is my IP address space and this is a circle. I'm marking 0 over here and going the way all the way around to 2 to the power of 32 minus 1. And suppose, let's say one particular slice of addresses has been given to, let's say, company 1. Okay. And let's say that another company has been given another slice over here. And yet another company has given another consecutive, a neighboring slice. Okay, and let's say that there are several of these. Okay, so these are slices, maybe they are class C or class B addresses and so on, given to different companies, right? And there is a particular company, let's say this is its IP address, this is its network. Okay, so there are several of these. Okay, and let's say that there is some network over here. And I want to reduce the routing table size in this particular router. Okay. So the simple way to do it, sort of the naive way, is to have one entry for each of these companies. Okay, and I put whatever the class C prefix, the class B prefix and so on, right? I put them all over here. But it turns out that all of them have the same next hop. So suppose this is R1 and this is R2. All of them have the same next hop over here. This is at R1. So can I actually combine all of these together to, let's say, have a single entry corresponding to all of them? And in this particular case, it may be possible because they are all consecutive, like all coming one after the other. So they all might form one large prefix. Okay, so if we can combine all of them into, let's say, one address, so that we have just a single entry, we reduce the size of this routing table, and that process is called supernetting. A practical example of supernetting. So let's say that there is an ISP, an internet service provider, and there are these various companies which are getting internet service from this particular ISP. And the first company has, let's say, an IP address which looks like this: 128.112.128. So this is the class C address. And the next one has the next slice, okay, and so on. And there are several of these. .135. Okay, so everything from this 128, 129 all the way up to 135. Okay. So what do these numbers look like? Let's just write them down. 128 onwards. So 128 is 1, 2, 3. Okay, this is 128. 129 would have just a 1 at the end. Okay, all the way up to 135. Okay, so this is 135. Okay. Now what we want to do is we want to combine all these consecutive slices of IP addresses into one large slice. So how do we do that? So notice that only these last 3 bits are changing. So these are changing, okay, but these are all remaining the same. So can I write all of these together as maybe one particular IP prefix? How would I do that? Well, clearly there is these first 2 octets are going to be the same. Okay, so that's straightforward. So let's say this is a common IP prefix. So it is going to be 128.112. What about this? So I want to only consider the first few bits. Okay, so I'll write out this full octet. Let me write out all of them actually. 128.0 even. So I'm writing all 32 bits. But I say that you consider only the first how many bits? So this is 8 plus 8, 16 plus 1, 2, 3, 4, 5. Okay, so this is the notation. Okay, so it's of the form a.b.c.d/n. So this is the general notation, and this n is saying how many bits to consider in the prefix. So it says consider the n leading bits to get the IP prefix. So when network engineers mention this sort of an address, they would call it a /21 address, or a /n address. So this is a /21 address. It's saying that out of these 32 bits, consider only the first 21 bits. And if the IP address, given a particular IP address, if the first 21 match with these first 21, then it matches with the IP prefix, that it belongs to that IP prefix. Okay. So if we are given an IP address, given a destination IP address, let's say D. So if, let's say, the first n bits of D match with the first n bits of A dot B dot C dot D, then this particular IP address D belongs to that prefix. Okay, and that is fine over here. Okay, because suppose in this particular example I get an IP address and it belongs to one of these different companies, it's definitely going to match with this particular prefix. Okay. So notice that all particular IP addresses belonging to this particular prefix belong to the combined set of all these different smaller networks. There shouldn't be an IP address missing, which, suppose there's an IP address which matches this particular prefix but does not belong to one of these companies, then that means we are not combining these IP addresses properly. When you come up with a common prefix for all of these together, it means that all IP addresses belonging to that prefix belong to one of these smaller networks. Okay, so in this particular case it does, it would belong to an IP address matching with the prefix would belong to one of these. Okay, so here I would have .130 star and so on. Right? Okay. So what are we going to do? So we want to combine these IP addresses into this prefix. So this particular internet service provider could advertise to the rest of the network, and it will do it in the BGP protocol, as we'll see later. So it advertises, it doesn't advertise these individual ones, it advertises 128.112.128/21. Okay, so since this doesn't belong to the prefix, okay, the first 21 bits only belong to these three octets, I'm leaving out the last octet and I'm writing it in this fashion. So this particular ISP is advertising, let's say, to the next autonomous system. Right? So each of these is an autonomous system. This too could be an autonomous system. So this autonomous system is telling the next one, I am advertising this particular set of IP addresses. It writes it in this prefix form. And all those IP addresses actually I can reach. If you send me a packet, I can deliver it to the appropriate destination. Okay, that's what an advertisement means. So this method of creating prefixes of arbitrary length is called classless interdomain routing. And it means that you can specify any prefix length. So the class A, class B and class C use particular prefix lengths, okay, whether it was 8 bits or 16 bits or 24 bits. But here you can use any prefix length n. Okay, you don't have to stick to those three. Okay. Which is why it's called classless. Okay, so in general, in the internet, we will be looking at these particular prefixes, and so this particular autonomous system, let's call it autonomous system 1, autonomous system 2, in its routing table will not have to have one entry for each of these. It will just have this IP prefix, and as its next hop it will have to put the appropriate router over here. Let's say that there is a router over here, let's say I call it R1. It will say that the next hop for this particular IP prefix is R1. Okay. So how exactly all of this is used in BGP we'll be studying a little bit later in the course.